Thank you, Prakash, for giving this opportunity. I am Shamik. I am from Aricent, basically from the CTO organization, working in different edge computing scenarios today. And primarily today I would be talking about the developer perspective of edge. So as we all know that edge computing would really succeed if a host of application developers join the edge computing ecosystem and start developing applications meant to run on edge. That means it demands low latency, it demands high amount of data, and its placement needs to be at the edge of the network. That kind of applications are hard to come by today, and in most cases we are sort of retrofitting ideas which may not be compelling low latency to run on edge and actually trying to prove edge as a concept. Having said that, Aricent and along with our clients, we have discussed and debated this with several developers who develop applications primarily meant for the mass market, like for example, the mobile applications running on our devices, or applications meant to run on drones, applications meant to run on robots. And we've tried to figure out a few questions of what are their primary requirements in terms of MEC platform, what kind of architectures, what kind of complexities they would like, what kind of architectures they require, and what kind of complexities they would like to avoid. As we all know, in MEC, particularly from a service provider's perspective, network function virtualization has turned out to be quite a complex solution. It requires a whole bunch of perhaps standardized descriptors and APIs and methods to onboard applications, and it has become quite complex. And if you look at an average developer who might be a small startup, or it could be a bunch of individual independent developers, the whole concept of NFV and the fact that it takes months to onboard applications and run them itself is quite daunting. So having said that, we tried to figure out what perhaps is required in terms of simplifying the network architecture or simplifying the service provider architecture for the developer. So it's not that we are simplifying the architecture in real life, but what we can abstract out from the developer's perspective and how can we make their life simpler. So that's core of my talk today. What we will cover here is perhaps a very short idea about the main drivers for multi-access edge compute from a developer perspective. And we look at some of the key questions from the application developers. Of course, there are many they have, but maybe I picked up 4 or 5 and try to see what it means in terms of having an edge compute platform. We would also look at the complexity of the networking in terms of edge compute and how we can abstract out that to the application developer. What exactly do we mean by developer experience in terms of edge compute? We'll talk a bit about that. We'll talk a bit about our platform and the storage problems in edge compute. And then maybe we'll look at some models on how to offload computing from devices to the edge. So having said that, let's start with the first slide, which talks about the main drivers for the multi-access edge compute. Now, this is, if you look at this picture, it looks like, from a developer perspective, why would they actually come to edge? I mean, today they are happy sitting in public cloud. They are able to serve the end consumer in a B2C model quite easily through public cloud. They might have to run 10, 14, 20, or maybe 100 workloads, but that's about it. They don't need to worry about regions. They don't need to worry about multiple distributed different edge computes across the geography. They don't need to run thousands of instances just to serve maybe a few customers. And secondly, the entire edge compute is so deep inside the service provider network, the developer has no access to it. So unlike in public cloud, they can actually log into a virtual machine and see how their application is working. But imagine this application is running deep inside the service provider network, somewhere deep near the base station or somewhere in the regional data center. How on earth can they even connect to that and see what's going on? And multiply that by thousands, then most probably this becomes an unmanageable situation.
So if you look from end-to-end perspective, what are the key things that the developer would like to come to Edge for? I mean, of course, the fact that there is a whole bunch of new kind of devices coming up, whether they are new kind of AR glasses, there are drones, there are so many new stuff coming in, that itself is a compelling requirement to perhaps come to Edge. The fact that they would get low latency access, maybe with 5G even lower. They can run applications just at the edge of the network. That means they could leverage only the access latency and perhaps a minimal platform latency. That itself is uh, quite compelling, but not perhaps enough if you look at the pains they might have to go through if they have to run their application on the edge. Uh, would they get the kind of seamless experience they have in public cloud? Can the easy access to cloud native toolkits, easy access to easy orchestration, not having to worry about monetization and monitoring at all because they have complete control over their workloads. In Edge, would they have that control in the first place? Or would the service provider be managing most of those workloads? How do they actually know how their application is performing? Many developers build applications and upgrade applications rapidly, maybe once in a day or maybe even many times in a day. Can the tool chains and the processes of the operator itself, uh, can it can it actually manage that kind of massive amount of changes happening over a short period of time? Uh, what are the mechanisms to offload compute from the device to the edge? I mean, is it so that we'll just stream data from the sensor or from a glass to the edge? Would we suddenly get into a situation where there are hundreds of devices sending uplink data and starts choking the network? Or are there some method where the application developer can run something on edge, something on cloud, something on device, and can selectively decide what to offload during the runtime of the application? So these are some of the for some of the key drivers. I mean, these perhaps we need to solve some of these problems. Some of them might have been solved already, in order to give a developer experience that might pave the way for developers to move towards edge more comfortably. All of these questions, I figured out that maybe five of them are the key questions to talk about. One, of course, is the developer experience that I talked about. So edge compute is deep inside the network, and how does the developer even reach there, or how do they even know what's going on? So we'll talk about that a bit in a while. So I'll park the first bullet for a moment. Now we'll look at a bit on the economics of edge compute. So say an average developer today, I mean, they might be running up to 100 or maybe thousands of workloads, but today most of them run between 10 to 12 or 20 to 40 workloads to serve their end mobile users, and these are running on public clouds. Now they can easily manage this. So you just have to log into a virtual machine, which they can from anywhere, from home, from office, or from their mobile phones or whatever, and they can see what's going on. They can look at their logs, they can do diagnosis, they can see how much money they made. Uh, Basically, they can monitor and monetize their applications quite easily from a central location. Now, when this comes to edge, the developer will have to run hundreds and hundreds of these workloads across data centers, across regions, across countries, or maybe beyond. And then there could be so that there are multiple service providers, so they might have to run variants of these same applications on multiple service providers' edges. So, for example, operator 1 has a different kind of cloud, operator 2 has another kind of cloud, and they might have to modify, change their SDKs or whatever to develop these applications individually for multiple operators. So suddenly when you start multiplying this by thousands and then you multiply with the number of operators, then this becomes a little economically unviable. And the fact that if you're running it as a server in each of these edge, and all the devices are connecting to that server, then you have to run the server even if there is one device using it. So for example, you have an AR glass. You made an application for an AR glass, and there are 100 edges. And if there are at least one user connected to that edge, you still have to run that server. So now multiply this for 365 days, 24/7. Suddenly the cost becomes much larger than what he's incurring today on the public cloud. Plus the public cloud, because of its scale, the cost itself is low. But when you go to the service provider's edge, the cost would be much higher. And the fact that you might have to run 1,000 times many workloads, this becomes a problem. So the cost per workload for a developer in edge compute is significantly high, or is at least projected to be significantly high when you compare that to public cloud. And so some kind of new mechanisms required. I mean, some kind of architectural platform solutions are required where perhaps you can run a container for each device. I mean, it's not intuitive, but you can. Say, for example, you have an AR glass, you're wearing a glass, you switch on the application, a container gets spawned which serves the glass, and then you switch it off, this container goes away. So you can actually try and figure out a cloud native model to have a one-to-one mapping of microservers with with devices. But that would mean that we are sort of sacrificing multi-tenancy. We have sacrificing the possibility of collaboration between glasses, collaboration between devices. How do you do notification? Which these are all features which a server architecture would have provided. In a microserver architecture, or microservice architecture as they call it, if we are going to run this faceless application for a few seconds or a minute, stateless applications, and if you want to collaborate in a multiplayer gaming where two persons are playing the same game and they're not connected to a common server, they all have their own for the duration they're playing, then this might not work. So therefore, there must be an additional need from the platform perspective to provide capabilities to do messaging, to do notification, to support multi-tenancy, to have this subscription publication kind of models built in, so that these devices can actually start to access it more like a server, but it's still running like in a faceless microservice model. So that's one of the key challenge. If you look from the end-to-end perspective, all the edge compute becomes inviable if the developers find it too costly. So some models are required perhaps to solve that. Then if you look at the kind of applications that require low latency, whether they are AI workloads or say a face recognition or something similar, or say an object recognition, or you're doing some kind of speech translation, or this may require hardware accelerators like GPUs. They are power hungry. They have a huge envelope of power requirements. They again pushes up the edge compute significantly, edge compute cost significantly up, and that passes on to the developer anyway. So how much of these accelerators are ready for prime time? Do you actually need them on edge, or you can sort of train them in cloud, infer on edge? And is the inference also requires GPUs? Maybe yes. Is this actually ready for prime time? Is this too expensive? Do we have problems in virtualizing it? Most of this is still open questions. We don't know the right or wrong answers. But many developers actually feel that they can really leverage low latency if they can build these kind of applications. And most of these algorithms which drive these applications are require some kind of specialized hardware accelerators. The other problem that we are looking at is what is the right edge for a client device. Now, imagine this situation that you are on a subway or on a train and you're connected to a wireless service provider's edge. You're playing a game. You reach your home. You connect to a different service provider over your Wi-Fi network, and your game stops working because your workload was running in somebody else's service provider's network, right? And you can't access the game anymore. Unless, of course, these two providers are the same providers and they have some collaboration, and those are a bit complexities from the operator's perspective. But an application developer can provide today a seamless experience to their end consumer if they run it on public cloud. I mean, if you are using a public network, you're sitting in a Starbucks, you're at home, or you're using a mobile phone, you're in a subway or in a bus or a train, you can still access the application. If you take that flexibility out from edge compute, then most likely the developers will have a second thought of building applications for edge compute. So we have to figure out the right edge compute dynamically. And this need not necessarily be service provider network always. It could be a local network of the city network, city data center. It could even be the public cloud based on location. So there must be a way to discover the right edge, or you must be able to provide a seamless experience to the end user based on location, latency, maybe hardware capabilities that the application requires, capacity of the edge compute in question, and on all of the above, maybe. So that's the other problem that perhaps we need to solve as a community. And then, as I was talking about in edge compute, today mostly we are downloading data, but in edge compute we expect the devices to upload data or uplink, have a huge uplink data. Now, if all the devices and all the glasses, everybody starts streaming data upwards towards the network, then there is a sudden deluge of data, and would the network be able to handle all of that? Maybe yes, we don't know, but would that mean that you would need some kind of complex queuing mechanisms or complex way of handling those incoming data on an edge compute? Well, there are some academic research going on that, but nobody really knows how much this would impact the platform architecture. Whether the current set of infrastructure solutions that we have, whether OpenStack, Kubernetes, and things on top of it, are they good enough to handle that? Maybe yes, but we haven't reached that stage yet where we can even simulate that kind of data. And are there other ways? And the previous speaker were talking about serverless. Can we actually provide a mechanism to the application developer where they can seamlessly move or do some compute on the device itself, and then offload a certain computing to the device on demand? Say, for example, he wants to do a matrix multiplication of two very large matrices, or wants to do some image processing on a certain frame that he captured. Can he just send that part to the edge and get that computed, or does he need to send the entire thing? We'll run a thin client on the device, and the heavy lifting is done by the edge. Ideally, yes, but in real life it might be complex, and from the application developer's perspective, it might be easier to do 90% of the stuff still on the device, and the 10% heavy lifting can be done on edge. Then what to offload, when to offload, and how to offload that 10% of computing from the device to edge is a critical question to get this edge compute to succeed. Finally, what happens if the edge goes down? I mean, this is a question which I repeatedly hear from developers. I mean, I'm running and the edge goes down. The connectivity to the public cloud is gone, or the connectivity to the internet is gone. Can we move the application somewhere? It's a stateless application. Can I launch it somewhere else immediately and get the device to connect to it? I don't know the answer. Maybe federating computing platforms is a way forward. Maybe having similar computing experiences running on device, running on the same platform, a piece of the same platform at least, running on the device, and running on the edge, and running on the public cloud, and you can able to federate, move around the workload seamlessly. You can decide to run the entire application on device if there is no edge compute, with of course some degradation of experience. Say, for example, the AR glass can get heated up, but if the edge is connected, then you offload that to edge. And if, for example, the edge is choked, you can move it to another edge, or you move it to a public cloud. So at least the end user experience can get deteriorated, but you don't have a complete failure of the service. So in order to have such kind of a decision making, that when to run it on device, when to run it on edge, when to run it on cloud, needs a fair amount of abilities in this orchestration system, or on the decision-making system of edge compute, to make that to work. Okay, so this is a rough idea of what we have been discussing with the developer community, and this sort of is a developer's voice, if you look at it. So this slide actually talks about the same problem that I was mentioning earlier. It's nothing different really. Just it gives you a picture of the complexity. So the developer is sitting somewhere here, actually, somewhere in the public cloud, on the internet, right? And he's onboarding the application to some portal which is running on the internet. He definitely can't directly launch an application on the edge cloud. I mean, he doesn't even know where the device is at that moment. So first of all, when he has onboarded this his workload on the edge, on the public cloud, there will be a device which will come up, and then the device will have to figure out which is the right edge. Somehow the device only the device knows this location at that point of time. the poor developer has no clue. I mean, he has hundreds of devices, doesn't even know where they are. So this device will have to figure out and negotiate with the network that, hey, this is the edge which is nearest to me, and maybe you need to run the server here, or the application server here. Then the service provider network will go to the public cloud, pick this workload up, and then drop it here, and then run it, and then you get this access, and then this device goes off, and then you still maybe cache the software here, but you stop the instance. And then this fellow takes a car, goes to his office, or takes a flight and goes to another city, goes to another edge. Then again, this whole rigmarole will have to start again. Okay, you discovered this is the right edge now. Yeah, and again, you pick it up from a central location, and you start running it here. Now, if this complexity gets, you start adding this, or you multiply this with number of device users in the mass market model, then this is pretty complex to solve, isn't it? I mean, for every time you need to figure out what's the right edge. Uh, One way is that the network is the boss and can always tell the device that, hey, this is the right edge for you. Or you can dynamically figure out when the device comes up through a set of APIs, through some kind of communication handshake between the network, you can figure out which is the right device. Maybe through probes, through a method of latency measurements. Maybe it's possible to empower the developer with some kind of SDKs and APIs to actually have an application logic to decide what's the right edge, instead of entirely depending on the network to tell them what is the right edge. Maybe at one point of time, the application decides that, hey, the right edge is the public cloud, and you might just run the device on the public cloud itself instead of edge. We don't know that. We don't know that. Lack of enough data, lack of ability to run this on a service provider network and figure out what is the right thing. So it's more on paper. We've done some simulations and figured out that yes, this is possible to discover the edge at runtime for the device, instead of the network commanding to the device that, hey, this is the right edge. The other problem that I was talking about, that there can be many edge platforms, right? There can be a platform for operator one. There could be a platform used by by an enterprise in a factory. There could be another platform which might be used by an airline in doing maintenance or doing some kind of networking applications in an airport. There could be a connected stadium which might be using a different platform. So there could be so many different possibilities of edge compute. Now, if an application developer is asked to build 100 such different variants of the same application, it might be a problem for him. I mean, it could be too much of a cost and effort to actually maintain that many variants of the same application, while he didn't have to do that if he was doing it from public cloud. And this is a problem because there isn't any standards, and there's not supposed to be any standards in innovative and disruptive technologies. So what is it that the application developer do? Uh, Possibly build applications as containers and hope for the best. Or maybe it might be a good idea to have a developer-facing services built in through some kind of a portal or a marketplace as a service, where the developers can sort of build their applications using maybe multiple SDKs or maybe a single SDK, upload these applications to this kind of a developer-facing service, and is able to do multiple things. Basically, you are able to do lifecycle management of the application. You can able to do lifecycle management of the developer itself, so they might be able to join, verify, test different edges, figure out what he wants to do. And then perhaps the most important thing is they are able to do some kind of monetization for their applications. Remember, monitoring is a major problem in edge compute. I mean, it looks simple on paper, but it's not. Hundreds and thousands of workloads, all from disparate, heterogeneous platforms, generating tons and tons of data. All of them have to be analyzed by the developer to figure out what went wrong or how much money he made. So there must be a way to federate or to aggregate all of this and provide the developer with what he needs. What kind of monitoring data he needs from this heavily scalable applications. I mean, there are like thousands running, and what kind of diagnostics the developer required. Those are very critical things to provide, and perhaps having or working towards or collaborating in the developer services model by organizations might be a good problem to solve, might be a economic problem to solve, given that the cost per workload will go significantly up if we don't solve this problem today. Uh, the second part is about in a service provider network's perspective. We know that there will be the usual wireless network functions. There could be multiple data centers, a layer one data center very close to the base station. There could be aggregation points. There could be regional data centers. There could be central offices, and these applications will move around. I mean, based on your latency requirement. If, for example, your application can tolerate 50, 60, 70 milliseconds, but is extremely mobile, then most probably would like to move the application a little behind in the network, maybe on a central office or maybe in a regional data center, so that you don't have to worry about migrating workloads from one base station to another as the device moves on. So say, for example, a drone and it's flying all over the Bay Area, or a certain city or certain location, and you start moving applications as it handovers from base station to base station, it's going to be a nightmare. So if it can sort of handle 70 milliseconds or 60 milliseconds or maybe 100 milliseconds of latency, then it's a good idea to push that application back towards the layer 2 or layer 3 data center, and you can avoid this continuous workload migration. But then there could be applications which might be more static in nature, but it demands low latency to an extent that it has to, maybe the SLA is somewhere around 15 milliseconds or 20 milliseconds. In that case, you would have to run the application perhaps in the nearest edge for the device. And imagine the kind of computing offload would happen. So the computing offload, a device offloads it to edge. If the edge is not capable or is congested, then what does it do? I mean, does it drop it, or it can move it backwards towards central clouds or towards regional clouds, or can it offload it to a peer, a nearby peer who might be relatively free? So there are multiple models actually to figure out how do we do this workload migration or this computation offload. Can this edge just act as an anchor and you actually run the application here if this is kind of if this particular edge is overloaded? Maybe yes, maybe no. Maybe there will be some impact on latency, and what kind of SLAs the developer sign up with the operator would actually determine that. But this is possible. This is possible to technically and theoretically it is possible to move applications from edge to a regional data center seamlessly across different edges based on what you want to do, what kind of QoS you are required to adhere to. And that is we have done some research on that, and very soon we'll be publishing some of the details that goes with it. But this is a critical problem to actually to solve from the platform perspective. The other important problem that we faced is on edge storage. Say, for example, there are certain applications which stores data, and the use case itself is that those data, if you transfer them to cloud, there is huge amount of backhaul costs. And if you don't need all of those data, maybe you just need to analyze them and drop that data, or maybe you need to use it for a such short period of time, and then you don't need the data. Then what's the point in actually sending all those exabytes or terabytes of data to the public cloud, or where you can store it forever for perpetuity? So you might as well, stock this data itself in the edge and then maybe destroy it or store it somewhere, or use it to do something. Say, for example, in an extreme case, there is an application which requires data to be stored and then wants to reaccess the data after a while. There could be reasons. Say a car might. I'm just giving an example. Now, if you store all of the data when he was near this edge, say one of the edges, say he was near this edge, and you store all the data here, and then this car sort of drives off to another edge, and he wants to access the data from this edge, and suppose there is no connectivity or there is no way to reach this old edge where he stored all of those data, then what do you do? or suppose this edge has gone down by that time and it's out of the network for a moment or so, then how do you reconstruct the data? There are some ways of doing it, which we think is that we can actually store the data in multiple blocks and using the concept of erasure code, but in a mode not at a node level, but more at a data center level, where you can actually store this data in multiple different data centers using by breaking them into some data blocks and maybe and a couple of parity blocks. And these parity blocks could be stored in each of these adjacent edges. So you can actually store one data block and one parity block in one data center, another data block, another parity block, or in another data center. And similarly, you can distribute these blocks across different edges. And when you want to reconstruct, all you need is the total blocks, but if some of the blocks are missing because the edge is out of connection, just having the parity blocks itself will help the application developer to reconstruct the stored data from which we might have stored in a different edge. So this is a very interesting way of actually figuring out, creating a fabric of data usage. The use cases are very rare, this kind of use cases, but it's still there. There's some developers who are looking for this kind of solution. This can actually be accelerated for low latency. We have recently demonstrated that by parallelizing erasure codes, which this method is called erasure coding, and parallelizing erasure code across multiple data centers and accelerating them through GPUs is actually a good idea. The other thing that I was talking about is the device to edge offload by offloading functions from device to edge. So suppose you are having a program that you're running on the device, and the developer is writing this application on the device, and there are some functions that are too resource intensive. It maybe would drain out the battery or something, or it may not be even feasible to run that particular algorithm or particular function on the device. Then you can actually offload that to the edge. So you might need a serverless architecture where you're sending an event to the cloud, saying that, hey, this is the function that I want to run, and this is the input data, the arguments of the function, and that function gets executed on the edge, and you get the response back to the device. This is critically to understand that this is between device and edge only. There is no way of going to cloud and coming back. You can do that like this in this picture. The device can go to an application on cloud, and the application on the cloud can use some kind of function as a service model to spawn functions parallelly. But at the same time, it is more prudent to actually offload directly to the device. So you can actually have the device somewhere here, and the device actually directly offloads the function to the function as a service of the platform, and you launch the function, and this function sends back the answer to the device itself. This is a much shorter loop, and this might be more prudent to do in a low latency environment. But then the problem is that these functions, if you use a Kubernetes, it takes 10 seconds or maybe a little less than that. So there's a cold start problem for such functions. So you might want to run the functions already or load these functions. In that case, what to load? What would you load? So we divided these functions into multiple layers. So there is, of course, the hardware and the software abstractions. There would be maybe some specialized kernel modules. There could be some intelligence layers where the actual application logic exists in the function. And of course, there would be some APIs to manage and handle all of these orchestration pieces. And this itself is a sort of a cell. And you might want to already start some parts of these cells when the device has camped on or device has started the application. So that you can accelerate the function execution faster as compared to doing it completely from cold start, and it takes a few seconds. Then the whole idea of having low latency falls apart. So there are some ways to do that. You can define all of these different layers through models, through an approach for stateful functions, and actually avoid the problem of finding a needle in the haystack, because this function runs for, say, a few milliseconds and it goes away. Suppose it did something wrong. How do you actually diagnose that? I mean, it stayed alive for so little time. You don't even know what happened. So there must be ways to offload or to at least store the logs or find a way to diagnose such functions, because hundreds and thousands of devices calling these functions randomly and quickly in a very high density, unless there's a way and you decompose these functions to multiple layers, it might be very difficult to figure out what happened. So these have to be defined through models and through say a container-based system. Just to summarize, we built this reference architecture for edge compute, keeping all of these problems that I talked about. So there is the a possibility of having a marketplace and a developer experience where application developers can actually have a common interface to run applications across edges, irrespective of what edge it is. Of course, this needs a fair amount of federating APIs in the southbound, but that's the problem we are ready to solve together with the ecosystem. There would of course be it looks very eerily similar to Etsy, but there will be application platforms which has to have the ability to do rapid upgrades like a DevOps model. It should be able to do multi-edge management or discovering the right edge for the device. The application itself can be three-tier. You can run something on the application client. So basically you can run something on the client, you can run something on the cloud, you can run you can run something on the edge, and you should be able to connect all of these together and run what is required where. Because the application developer finds it extremely expensive to run everything on edge, so he might want to run only a part of it. And then of course you need to support virtual network functions, you need the offloads, the compute offloads, and then of course you need this entire thing to have some kind of a microservice model running perhaps on containers. We also plan to support enhanced machine learning by supporting multiple hardware abstractions and so on and so forth. Right, so that's all from my side. I might
Thank you, Shamik.
be a minute over. Yeah.
Thank you very much. I know it's early in the morning in India, but appreciate you dialing in and giving the audience
Thank you
a
very
great
much,
presentation.
and
Thank you.
thank you very much for the opportunity and for people listening to me patiently. Thank you very much, and we'll definitely be in touch.
Absolutely. Thank you.